Just a quick check, are we live? Just wanna get a quick sensing of the chat room. Alright, say hi in the chat. If we are live, are we live? Just want a quick check. Are we live at the moment? Maybe someone can help with the technicals in the future or something. Okay. Yeah. Okay. Are we live? Technically, still have 2 minutes. We still have 2 minutes, but yeah. We will need to wait for that. Okay, I think my guessing is that, my guess is that it will be live at 10:30 flat. So we'll say hi in the chat in a moment, okay? Yeah, I'm gonna depend solely on the chat for any kind of interaction that we have today. Welcome everyone to the stream, to discrete math, and we're looking at sets, relations, and equivalence, relations and partial orders today. Alright, are we live? Are we live? Hello. Okay. I don't think we're live yet, but we're gonna get there. I think we're gonna get there soon. Yeah. Okay, are we live? Just want a quick check. Are we live today? Alright, if we are live, can give an indication in the chat. Alright, we are live. Welcome everyone to the stream. And today we're going to look at sets, relations, and equivalence relations. As planned, the plan here, hey guys, the plan here is to look at some questions that have not yet been online yet. We're gonna look at those questions, and then we'll proceed with Q&As. We're gonna go with question, Q&A, question, Q&A, and we're gonna go back and forth. Okay, so let's start off with a question pertaining sets, sort of like a warm-up question. We are given that A and B are sets, and we claim that if we take A exclude B is the same as taking A exclude A intersect B. So the idea is almost that, okay, in terms of a Venn diagram, we are looking at A exclude B. This region is the same as taking A excluding the intersection. Right? That's the intuition behind the question before we actually go ahead and prove it, because usually it's a good idea to first have some vague notion of whether you're right or wrong before you go ahead and prove something. Alright, so we're gonna go and prove our result. For simplicity, we're gonna assume that we have a universal set U. Hopefully this works out. And let's see what ideas we can use here. Alright, so the first observation, and I believe we've used this, or at least we've proved this before, either in one of the streams or in the tutorials or even in the lectures. We have proven before that A intersect B is a subset of B. Right? Now, what exactly do we need to do, by the way? Since we're proving set equality, we need to prove that the left side is a subset of the right side and vice versa. Okay? We need to show that that we get two-way subset inclusion. So we need to show this subset inclusion as well as this subset inclusion. So the trick that I'm going to apply here, actually it relies on one of the tutorial results, and it turns out that if we have one set being a subset of another set, the complement, if we take complements on both sides, we're going to reverse the subset inclusion as follows. Right? So in fact, that actually establishes the first subset direction from A exclude B to A exclude A intersect B. right? So now we need to go ahead to prove the other inclusion. We need to go ahead to prove that this set over here is indeed a subset of this set. Now for this one, I'm pretty open to having different possible solutions. But that being said, we're just going to prove it using element chasing, because element chasing is one of these methods which you can't really go wrong with. Right? So we're gonna fix some element x inside A exclude A intersect B. What's our goal? Our goal is to show that x belongs into A exclude B. So we're gonna chase the element from the A exclude A intersect B all the way to A exclude B. Now what does this mean? This tells us that x belongs to A and x does not belong to A intersect B. Alright, that's what it means. Well, what does this mean? Maybe I can write it in this form instead. What does this mean? Well, this means that if x is not in A intersect B, it means that x is either not in A or x is not in B. A few ways to justify this. There's De Morgan's laws. There are a few different approaches to that. But we're going to distribute the the conjunction over the disjunction. And by the way, I believe there is a set theoretic way to prove this result. I'm not intending to do that at the moment. But maybe someone could suggest a set theoretic result in the comments. That would be awesome. Alright. Oops, I made a typo here. This should be in A, not in B. Now, the first bit over here actually is a contradiction, right? Or rather, it's gonna be false, because this is a proposition that sort of its proposition and its negation. So we have a negation law that tells us this guy is false. This junction with this thing here, which tells us that, well, if you take false disjunction anything, the identity tells us we get x in A and x not in B. This is another way of saying that x belongs to A exclude B, which is precisely the goal which we were working towards. So that's how we can think about element chasing. We fix an item from the left set and we chase it all the way to the right set. I believe the set identity approach. Let's do a proof of set identities before going into the Q&A. I think that's actually a good exercise as well. So the claim, right? The claim is that A exclude A intersect B is a subset of A exclude B. So let's prove this using set identities instead of element chasing. We can start off with the left side. And complements are not really nice to work with, so we're going to convert this into we're going to convert this using the complement set and the intersection. We can apply De Morgan's laws, which is actually, if you think about it, it really is actually fundamentally the same proof as the element chasing. But okay, I'm just going to do this for benefit. We can distribute the intersection. We notice that a set intersecting its complement will always give us the empty set. And taking empty set union any set gives us that particular set itself, which is basically A exclude B. It's kind of weird because I noticed this is actually a much more efficient proof because it's all set equalities all the way. I didn't actually have to prove two-way inequality, two-way subset inclusion, but oh well. That's awkward and embarrassing. So it's all good. Okay, so that's it for this particular question. Let me open the questions now to the floor, and you guys can give your questions, and we will sort of go back to solve one of those problems later in 30 minutes time. Okay, so chat, take it away. Is empty set same as the set containing the empty set? Well, so here's the question. Well, on the left, now when we use the empty set is actually a shorthand notation for this particular set. So we can make a replacement here. So I think from this, it should be pretty evident that the set on the left contains no elements, and the set on the right contains one element. So clearly, they can't be equal to each other. How do we get the green part? I believe this is from one of our tutorial results, where if you have, I think we have proven this result. If a set X is a subset of Y, then the complement of Y will be a subset of the complement of X. I believe we proved this somewhere. One of my previous videos, I've done it as well. Probably the sets one. Yeah, okay. So that's that. For everyone else, just enjoy the music. Enjoy this playlist. I believe the link is in the description. Go and check it out. I enjoy studying to this music every now and then, when I used to be studying. I'm just reconsidering my life goals. When do you use without loss of generality? Suppose that A and B are in the context of some universal set. I believe you can use that whenever you want to use set identities to prove things. So a bit like this, right? I should say that, okay, maybe I should put here, without loss of generality, suppose A and B belong to some universal set. And the reason why you do that is so that you can define the notion of A complement. A complement is the reason why you want to use this disclaimer, essentially. Yeah. If a set has this, then is A exclude? Okay, let's take a look. Suppose A is, well, do we mean that A contains these items, or is A just the set itself? Right? So let's see. If A is equal to this, then A exclude the set containing the empty set. It means I'm taking away the element, the empty set. So I'm essentially cutting this out. So I'm left with the set containing 1 and 2. Of course, you could sort of use this in a more relaxed notion. This works as well. I believe we have proven, I think we have proven that if you have a set of this form, then the complement will be a subset, right? Okay, we're gonna look at relations in a moment, but for now, I think we've proven this result, but I can prove it again. It's not a very difficult challenge, right? So, okay, so proof. Suppose, right, what's the goal? We need to show that Y complement is a subset of X complement, so we're gonna fix some element W inside Y complement, and the goal is to show that W is in X complement. Well, we are given that, well, okay, if Y is in Y complement, if W is in Y complement, then this tells us that W is not in Y. And at this point in time, we might be a bit stuck. Well, we can think about what it means for X to be a subset of Y. Okay, this means that no matter which item I have, if the item belongs in X, then it belongs in Y. This is equivalent to saying that no matter which Z I have, if Z is not in Y, then Z is not in X. In particular, since we're using W, we can use this result to conclude that W is not in X, which means that W is in X complement, which is the goal that we were looking out. So that's a very quick proof. If you're not convinced that it's from the tutorial, here's a very quick proof that that this property works. Okay, so we will be looking at relations in a moment. I mean, not really. I mean, we're doing the L-Tromino question in a moment, which is not really relations. Yeah, fine. Let's look at relations. Properties of a relation over R squared or Q squared. Okay, so we have to, when we say a relation on a set, right? A relation. Let's look at the definition. Right? We say that R is a relation from A to B precisely when it is a subset of A cross B. Right? It's a subset of connections from A to B. You can think of it as recipes in A that give you dishes in B. So that's the sort of that, and we say that R is a relation on A precisely if it's a relation from A to A. So in particular, we say that R is a relation on R squared precisely when R is a subset of R squared cross R squared. Now what that may look like in geometrically, some people might try to extend this to 4-dimensional space, which is a little bit difficult to visualize. I can't do it. But I think of it this way. I think of it essentially as, here are some points in 2-dimensional space. Here are some other points in 2-dimensional space. And R represents the different arrows that one could sort of connect from one space to the other. So I wouldn't say there's a very clean visualization for it, but once again, you can think of a space here. These are R squared, these are R squared, and relations are the connections between these two items. You sort of have a recipe over here that you can create a dish over here, right? So that's just basically that. Of course, the particular shape of R squared, it's like a 2-dimensional piece of paper. Right? It's essentially a 2D plane. Yeah. I believe any other sets related question in terms of the tutorial questions I've covered in the other stream, so you can go and check that out. I think it's called what even is an infinite union. I think that's the one. Yeah, so feel free to look at that. If A equals to 1, 2, is this set defined? Well, it is. Well, you're just saying A excluding the set containing nothing. So you're going to remove no items, which basically means you're just going to get 1, 2. Right, because you take a set, you exclude it, you essentially get the same thing. You're removing no items, fundamentally. Well, but you've already... If you mean that, will the empty set be a subset of A? Yes, because you can choose no items. But is the empty set an element of A? It is not an element. Where is the empty set? There's no empty set here. Right? So we know that the empty set is a subset of A, but in this context, in this particular context, the empty set is not an element of A. Alright? There's a subtle notational distinction. Yeah. Okay, looks like we're actually going much quicker than I thought. So, you guys got any more sets related questions? If you guys are good, we're actually gonna go over to a we're gonna do the fun little L-Tromino tiling trick in a moment. Alright, so that one's pretty fun. Apparently I haven't recorded that, so I'm gonna record it now. Yeah. Anyone has any other questions at the moment? Alright, if you guys get any other questions, you can feel free to raise them after we look at this little fun little puzzle over here. Right? So here's the question. Suppose we have this setup. We have this setup. And we have this setup. Okay, we're gonna look at the universal set question in just a moment. So we're gonna do that after this one. Right. Essentially, the universal set allows you to use complements. If you don't have the universal set, this doesn't make sense. Oops. Oops. Okay, so here's the deal. This setup, this piece over here is called an L-Tromino. This is called an L-Tromino. Alright. And what we're gonna do is play a little game. You are going to decide one square to remove from each of these pieces, and I'm going to cover the rest of them using L-Trominos. Alright, that's the deal. Okay, so anybody want to suggest which piece should we remove? Which row and which column should we remove? Right? This is, for example, the first row, first column, I'm going to remove this particular piece. First row, second column, I'll remove this piece. Okay, so come from the chat, right? Someone can suggest which piece should I remove from this first square. Right? Which piece should I remove from the first square? You'll be surprised to know that I actually can always do it, but you know, just for a little bit of interactivity today, which piece would you guys like to remove from this square? Alright, let's go for 1-1. So let's remove this. I think it's pretty obvious. I'm going to cover it with this L-Tromino here. Alright, that was pretty easy. Now how about this one? Slightly bigger square. Alright, which piece would you like to remove? Feel free to choose a row and a column. Alright, and then we're going to go with it. 3-3. So let's get rid of that. I'm going to cover it this way. And finally, a much bigger set. You might think this is a little bit harder, and you're not wrong, but it's not as hard as it seems. So pick another square. Choose any square you want. I don't really care, because I should be able to cover it if I did it properly. That sounds pretty arrogant, but yeah. Alright, 7-6. Okay, 3-7 and 7-6. I'm gonna choose one. 7-6 is 7-6. Okay, so it's this one. 3-7 is gonna be 3-7, so it's gonna be this one. Either are pretty easy for me. I think 3-7 looks a little bit more challenging, so we're gonna go with that. Alright, you're worried about I saw a comment about induction, right? Don't worry about induction, at least for this particular round. And also for this question, when it comes to induction, you don't have to worry so much, because these kind of novel questions are not really what we are looking to assess, but this is meant for exposure to the idea of induction. Okay, so I'm gonna cover it in this manner. Okay, I'm gonna put a piece there, and then I'm gonna cover the rest in this manner. Okay. And for this last one, is a little bit tricky. I'm doing that. So you might be wondering if this is always possible, okay? And essentially, we're gonna use induction to prove that this is always possible. Now, what's the setup? The setup is that it's always possible to do this when this length over here is 2 to the n, and this length here is 2 to the n. Okay, so we're going to prove this by induction. So P of 1, we need to check that it works for the 2 by 1 times 2 by 1 situation, which actually is already given to us over here. Right. Now we need to establish the induction step, which is to say that for any k in the, say, positive integers, right, pk implies pk plus 1. What does pk in this context mean? It means that the 2k by 2k guy is tileable. So we want to show that the 2k plus 1 by 2k plus 1 is tileable. Right, that's pretty important. So we're going to draw a bunch of things. I'm going to split this up into 2, because if you divide by 2, you're going to get 2k's. And 2 to the k is really, really useful. Because we already know that in each 2k by 2k square, you can cover it using L-Trominos. So, let's get rid of one particular square. Get rid of any square you want, okay? Let's just say we're going to get rid of this particular square. Right in the middle of the board. It's pretty annoying. Can we cover the rest of the squares using L-Trominos? The claim is that this is possible by induction. So we're going to, here's the trick, I'm going to remove these 3 squares over here. And since I've removed one square from a 2k by 2k block, this guy is coverable. Since I remove a square from the 2k by 2k block, this guy is coverable. And since I remove a square from the 2k by 2k block here, awkward, this guy is coverable as well. Finally, for this particular block, we remove this piece. So that is coverable as well. All that remains is the middle piece right here. Is this middle piece coverable? Well, it's in the shape of an L, so we've covered it. So therefore, this works as well. Okay, now this is the essence of the proof. You can formalize things if you wish in terms of coordinates. It takes a bit of effort, but it is possible. And we won't require such deep formalisms for this particular proof. Awesome. Okay, so that's the induction question. Back to the floor for a few more questions before we look at one more final question, final sort of interesting question pertaining partitions and equivalence relations and whatnot. So there's that. Right, back to the floor. Question time. And for everyone else who's just chilling, enjoying the music, it's good. I like it. And I have good taste. Feel free to ask, okay, what's this? What does it mean if you assume universal set? Essentially, if you assume universal set, this notion makes sense. If you do not assume universal set, this notion does not make sense, because this set is by definition the collection of items in the universal set that don't belong into the set A. Okay? So that's what it means. That's what it means. If you don't assume a universal set, this particular set does not make sense. And you can't use all of the manipulations. Right? Because if you want to use set identity manipulations, you probably want to use this set complement pretty often. Alright, any other questions from the floor? without loss of generality. So without loss of generality, I always strongly discourage anyone from using it in this particular module, because as you can tell, most people have no idea what that means. Okay, but let me give an explanation of how one can use without loss of generality. Okay, let me give a very quick example over here. Okay, so let x and y be distinct rational numbers. Okay, which notation is stricter? The problem is that the fact that we're thinking about stricter notation implies a sort of a misunderstanding of the notation. Okay, but we're gonna explain that in a moment. Now, x and y be distinct rational numbers. What does that mean? Okay, so the claim is that there exists a rational number such that z lies between x and y. And what's the proof of this claim? Well, do we know whether we say that x and y are distinct, but do we know whether x and y, which one's bigger? Because we claim that there are two distinct rational numbers and one is bigger, and there's a rational number in between these two. How do we know which is bigger? Well, we don't actually know, right? But since x is and y are distinct, we know that x is less than y, or y is less than x. And if we think about it, the argument works in both ways. So mathematicians are really lazy. We like to say, okay, let me just do the quick proof. In the first case, choose z to be x plus y over 2, then x will be less than z, less than y. Of course, you need to do some algebra here, right? And it turns out that z equals to x plus y over 2 as well. In fact, I'm going to use y plus x over 2, which implies that y is less than z less than x. Now, if you look very carefully at the argument, this argument and this argument is exactly the same. It's exactly the same. In other words, these both cases are not really that different. So we like to say, without loss of generality, assume x is less than y. Because in the other scenario, we're going to use the exact same proof. I do not recommend it for this module because for many people who are new to math proofs, it's not entirely obvious when the proof is the same. So I don't recommend without loss of generality, unless you know that the proof will be the same. Okay, on strictness, the problem is that that we don't even have a notion of which is more strict than the other, right? We say that A is a subset of, or rather, we say that the set A is a subset of B precisely when, no matter which item you are dealing with, if it belongs in the left guy, then you get it belonging to the right guy, right? So the problem is that subsets compare, or rather, subsets are written in the context when you have a set being a subset of another set. Element of is an object being an element of another set. Does that make sense? So you have to know the difference here. Okay, you have to know the difference here. The lecture notes say non-strict partial order and non-strict total order. The difference between non-strict versus strict. I think what they mean here is that there's a difference between, say, the strict inequality and the non-strict inequality, right? I think that's what they mean here. So that's the main difference. The problem, of course, is that this proposition is false, but this proposition is true. So the strict inequality is never reflexive, right? Which sort of ruins the whole partial order definition, if you would. So that's why we use the non-strict inequality. Okay. Any other questions? Of course, you can feel free to raise them at any point in time. Right. Okay, final call. 5, 4, 3, 2, 1. Alright, so we're gonna look at this one more question. We're gonna look at one more question. This one is a really interesting question involving equivalence relations and partial orders. So when you use double arrow, when you use equal sign, double arrow or equal sign. Equal sign is equality, but double arrow is when do you use this guy versus this guy? As far as this part of the module is concerned, I will always use this. Okay. Between logical propositions, I'll just say this is equivalent to this guy. I'll always use the double arrow just to make things easier. Okay, so we're gonna look at this last question and then we're gonna open the floor for Q&A once again. So this is a really interesting question. We are given, okay, that this guy is an equivalence relation on A, and now we claim that this particular set forms a partition of A. Now, this here unpacks a bunch of different ideas at once, right? Because firstly, what on earth does this refer to? And secondly, what on earth does this refer to? Okay, so in my classes, and some of you are aware, I've recently used this analogy called the pizza analogy. Okay, so here's a pizza, and suppose you have the items 1, 2, and 3, and 4, and 5 like this, and you cut up the pizza in this form. Well, what do you notice about the pizza? The first property that you notice about the pizza is that no matter which pizza slice you use, let's call it C. No matter which pizza slice you pick, the pizza slice is non-empty. Right? Every pizza slice is non-empty. Secondly, whenever you have two pizza slices, right? Let me just write it this way, sorry. Whenever you have two pizza slices, right? If these pizza slices are different from one another, or rather if they are different, right? If they're different pizza slices, they never overlap. Now what that means is that if the two pizza slices do overlap, then they must be one and the same pizza slice. And thirdly, we also notice that if you take the union of all the pizza slices, you get the whole set. These three properties of a pizza slice, of the pizza slices, are precisely the properties of a partition of A. So in fact, we need to show that this guy forms a partition of A. We need to show that if we replace each of the collection of sets, all of the sets inside this guy forms a partition of A. Now that still raises the question, what on earth does this notation refer to, right? Now this notation refers to the collection of all the different equivalence classes. What are equivalence classes? I'm gonna talk about that in just a moment. If you look carefully, this pizza slice, we call this the equivalence class containing 1. We notice that it contains a bunch of other items, 2 and 3. And roughly speaking, this pizza slice tells us that 1 and 2 are related to each other, 2 and 3 are related to each other, 1 and 3 are related to each other. In some sense, they're all quote-unquote equal to each other. It's like a generalized equality. And so we can say that this guy equals to this equivalence class equals to this equivalence class. All of these guys refer to the set containing the elements 1, 2, and 3. So, once again, this notation refers to the collection of elements that are related to X. Okay, so that's what that's all the notation, right? That's just notation. That's not like the actual proof. It's quite notation heavy, right? But that's notation. So we need to prove this claim. What is the third point in green meat? It means that when you take the union of all the pizza slices, you throw all of the ingredient together, you are just gonna get the entire pizza slice. The entire pizza, right? So when you take the union of all the pizza slices, these are the unions of the pizza slices, you will get the whole pizza. So on that note, let's go ahead to prove each of these claims. So what do we need to show? We need to fix some set inside this guy, a quotient tilde. This guy is called tilde. Fix this item. The goal is to show that this pizza slice, or rather this equivalence class, is non-empty. So what does it mean? We need to find at least one element that belongs inside this particular equivalence class. Well, which element will be related to X? Well, the tilde is reflexive, so it means that X must be related to X, right? So since tilde is reflexive, X is related to X. X tilde X holds. But that means that the element X belongs in the class containing X. Of course, this seems relatively obvious, but we still ought to prove it. Which implies that the class containing X is non-empty. Okay, so that's the first thing that we needed to check. In this case, we are letting C equals to A quotient tilde. Okay. Now we need to prove the second bit. So let's fix two equivalence classes inside A quotient tilde, and we are gonna suppose that these guys are non-empty, right? Okay, I'm applying that right now actually. So hold your horses, we're gonna get there. Equivalence classes essentially are generalized equal symbol. Partial orders are generalized less than equals to. Okay, we're gonna look at some of the applications in a moment. For now, let's finish up let's finish up this proof. The goal is to show that X equals to Y, right? And I think some of you who were in the class would have known how we prove this, but let's just prove it here once again. How do we prove set equality? We need to prove two-way subset inclusion, right? This way and this way. Right, so now what we're gonna do, let's first prove this bit over here. So we're going to fix W in the class containing X. The goal is to show that W belongs to Y. It might be important to decode what these things mean. So this means that W is related to X, and this means that W is related to Y. We might even want to visualize this. Alright, so let's just visualize it in a diagram. There's W. Oops. Here's W. Here's X. Here's Y. Here's Z. Well, not Z, but it's just Y. Our goal is to show that W is related to Y. That's our objective, right? That's our objective. And at this point in time, we probably get stuck. It's actually not entirely obvious how we ought to continue at the moment. And this is where we need to ask the question, what have we not used in the question? If we think about it really hard, we have not actually taken advantage of the fact that that these two sets are non-empty. So using this fact, we can show that this implies that there exists a Z in A with the property that Z belongs in the equivalence class containing X, and Z is related to Y as well, because Z sort of belongs in the other class. In other words, you get these two arrows. Now, what's the intuition here? The intuition here is if we can build a bridge like this, then we can draw a bunch of arrows, we can chain these arrows by transitivity, and we are good to go. So is this possible? Is this possible? Well, we know that tilde is symmetric, and this implies that X will be related to Z. So this allows us to chain up these guys and say that by transitivity, W is related to Y, which is precisely what we aimed to prove. So all that has done is help us prove that if this is non-empty, then we get this subset relation, right? So we have proven this bit over here. However, if we think about it, you might be wondering, do we need to work hard at proving the reverse direction? Turns out, if you think about it, this implies that the set containing y and the set containing x is also non-empty. Which means, by the exact same argument after a bit of relabeling, y must be a subset of x. And we are done. This actually proves the reverse direction. So it's pretty fun. It's pretty fun. Okay, we're gonna continue with the proof, but let me just answer this question. What's the concept of equivalence classes? Generalized equalities. What's partial orders? Generalized less than equals to, right? So you have equality, right? Roughly speaking, let me just address this question here. The key properties of equality are the fact that any item is equal to itself. If you get one way equality, you get the other way equality. And if you have two things being equal to each other, you should get sort of a transferring of equalities. So equivalence relations generalize these notions. It's just a generalization. So we can write, instead of equal sign, right? It could have been some other kind of relation, say tilde, and that's the equivalence relation. Right? Of course, you can talk about equivalence classes as well. Likewise, for partial orders, we are generalizing the less than or equals to notion when it comes to real numbers. Right? So every number is not more than itself. If two numbers are not more than each other, then they must be the same number. And finally, if you have two pairs of numbers not more than one another, you can chain them up one at a time. Okay, so that's the idea of a partial order. Alright, back to our proof. Now our final claim. Final claim. If we take the union of all of the different equivalence classes, or you can think of it as pizza slices if you would, you get the whole thing. Alright, so that's the claim. So once again, this is a we need to prove set equality, so we need to prove two-way subset inclusion. The first way, I'm gonna pull off a little cheat code over here. Okay, we know that this is by definition a subset of A. Right, we've already defined this set to be by definition all of the items in A that satisfy the property, which means that it's a subset of A. Well, I'm going to take the union across all of these items. But on the right side, the union of one particular set is just a set itself. So that's it. That's it. I should probably use green to describe this. And then we're going to go in the other direction. So finally, for the other direction, let's fix an element W in A. Our goal is to show that W belongs into the union of equivalence classes. And perhaps a more sort of user-friendly way to think about it is that, well, we need to find one of the items such that W belongs inside the equivalence class. Then that way it belongs into the union. All is well and all is good. Well, we know that if W is in A, we've already seen that W belongs into its own equivalence class, right? By the previous argument. This is not very convenient. This is very not convenient. Okay, are we good? Is the lag cleared up? Has the lag cleared up? Has the lag cleared up? I believe there was a lag just now, and there was That was not very convenient. Okay, so well, that's not very convenient. Okay, so essentially, that's the proof, and yeah, we have shown that we get a partition because it essentially fulfill all of our pizza requirements, if you would. So a partition is essentially a bunch of pizza slices, right? Each pizza slice is non-empty. They don't overlap each other, and of course, they give you the entire pizza. Right? You take the union, you get the entire pizza. So that's that. Now, of course, I have a few follow-up questions which I am gonna just put here. It's a really, really interesting question. So suppose you have a partition of A, right? Hello, are we good? We're good. All right. Okay, so exercise. Here's an exercise. Show that there exists a relation, an equivalence relation on A with the property that A quotient this relation equals to C. So that's that. Okay, one more exercise. I'm gonna go into the question in Q&A mode. So one more exercise. This one actually relies on functions. So suppose f from A to B is a surjection. Okay? Right? Prove that there exists a partition, or there exists an equivalence relation on A, okay, and such with the property that you can find a bijection G from A quotient D tilde to B. Okay, so that's just a little exercise you can try. It's a really it's not an easy exercise, but it's something worth looking at. So here's another exercise. Okay. All right, so back to the floor for Q&A, and we're good to go. So the solutions proves every element is in some element of C instead of the green point. Every element of A is in some C. I mean, that's what we did, right? Every element in A is in some C because in some this item is the C in this context. So every W is in some C. So that's what we did. We found an X such that W belongs to this X. This is the C that's required. And since it's for any element, that's where we fixed this any element, because W could have been any element that we wanted. The entire argument would follow along as per normal. Alright. So can we say if the former is true, the latter is true? If the former is true, then the latter is true. Oh, I mean, we had to prove it, right? And we actually had to prove it, right? We actually had to prove that it's true. Yeah. What is symmetric and anti-symmetric? Symmetric is the property that if you swap two things, you get the same thing. So symmetry refers to the fact that if A and B are related, for any A and B in the set, if you swap the B and A, they are also related as well. Anti-symmetry means that if you have relatedness in this manner, if you have both elements relating to each other, you must get the same element. So you can think of it this way. I like to think of it as symmetry as two-way streets. Anti-symmetry tells you that the only streets are one-way, if you include loops as one-way streets. Yeah. So symmetry is like two-way streets, and anti-symmetry is like one-way street. Alright, back to the floor. Back to the floor. Hope that helps. Hope that helps. What are the characteristics of a partition again? Yeah, I think I went a little quick there. So a partition is like a pizza. It's like a collection of pizza slices, right? Firstly, for any pizza slice you have here, this pizza slice is non-empty. Every pizza slice contains at least one topping, right? Secondly, if you take two pizza slices, if there are different pizza slices, they don't overlap. And what that means is that if they overlap, they must be the same pizza slice, right? Finally, if you take the union of all the pizza slices, ideally you should get the entire pizza. Right, so that's how I think about the definition of a partition. So I'll just recall it off the top of my head. I use this pizza slice analogy. I've come to notice, and I mentioned this a few times, but I've come to notice that food and math go really, really well together as analogies. So there's that. For functions, I've been abusing this recipe dish analogy for functions. So that's fun. But those are the characteristics of a partition. Right? It turns out that equivalence relations and partitions have very close connections to each other. Think of pizza slices. That should help. That should help. Okay, so once again, this notation here refers to all of the items in the set that are related to this guy. Right? That's what this means. Okay, yeah, so there's that. Yeah, exactly. The entire pizza is essentially the entire set. Yeah, exactly. The entire pizza is like the set of all the different possible ingredients. Yeah. The part where I took complement at the start of the video, so I'm gonna leave this as an exercise, which I've proved in this video actually, that if you have the set X being a subset of Y, the complement of Y will be the subset of the complement of X. Okay, so I use this particular property in the proof. I done it just now, but you can go and watch this video again if you wish. Yeah. This is called a definition. Whenever I'm introducing a new terminology, I always use a definition. Yeah, so this is just a notation saying I'm going to define this symbol on the left to have this meaning on the right. That's just a definition. Yeah. So it lets you know that you're reading something new for the first time. Right? It's like, oh, this is actually something new. It's not just a symbol I'm supposed to know. It's a new symbol that I'm introducing for the first time. Yeah. Alright, any more questions from the floor? Once again, you guys you should practice all of the different further exercises because having some calculation aspects would help. Yeah. Is it the same as left-right arrow is between logical identities. This over here is an object. This is an object. This is not an identity. This is not a proposition. Right. So it has a similar meaning, but we have to be careful because this is an